Welcome to the next chapter 10 of 11th Physics Mechanical Properties of Fluids. In this part, you will learn about fluids and pressure. Fluid is a substance that can flow. It ultimately assumes the shape of the containing vessel because it cannot withstand shearing stress. Thus, both liquids and gases are fluids. Important characteristics of fluids. The atoms or molecules in a fluid are arranged in a random manner. A fluid has no definite shape of its own. It ultimately assumes the shape of the containing vessel. So, a fluid has no modulus of rigidity. A fluid can withstand a force in a direction perpendicular to the surface. So, a fluid does have a bulk modulus of rigidity. As shown in the diagram, when we pour water in a tumbler, it takes the shape of the tumbler. Pressure. You know that whenever a liquid is in equilibrium, is having a fundamental property that it exerts a force on any surface in contact with it, and this force acts perpendicular to the surface. The total force exerted by a liquid on any surface in contact with it is called thrust. It is because of this thrust that a liquid flows out through the holes of the containing vessel. And the pressure at a point on a surface is the thrust acting normally per unit area around that point. If a total force F acts normally over a flat area A, then the pressure will be force upon area. If the force is not distributed uniformly over the surface, then the pressure will be different at different points, and we will calculate the pressure by calculating dF by dA. For example, consider a very sharp needle which has a small surface area, and consider a pencil whose back is very blunt and has more surface area than the needle, as shown in the diagram. If we poke needle in our palm, it will hurt as needle gets pierced inside our skin. Whereas if we poke the blunt side of the pencil into our hand, it wouldn't pain so much. Because area of contact between the palm and the needle is very small, and therefore the pressure is very large. Whereas the area of contact between the pencil and the palm is more, therefore the pressure is less. When an object is submerged in a fluid at rest, the fluid exerts a force on its surface. This force is always normal to the object surface. This is so because if there were a component of force parallel to the surface, the object will also exert a force on the fluid parallel to it. And as a consequence of Newton's third law, this force will cause the fluid to flow parallel to the surface. But the fluid is at rest. This can't be practically possible. So the force exerted by the fluid at rest has to be perpendicular to the surface in contact with it, as shown in the diagram. The normal force exerted by the fluid at a point may be measured. An idealized form of one such pressure measuring device is shown in the figure. It consists of an evacuated chamber with a spring that is calibrated to measure the force acting on the piston. This device is placed at a point inside the fluid, and the inward force exerted by the fluid on the piston is balanced by the outward spring force and is thereby measured. Some more points about the pressure. It is a scalar quantity. Because the force here is not a vector quantity, as we have taken the component of force normal to the area. Dimensional formula for the pressure is ml minus 1 T minus 2. SI unit Newton per meter square or Pascal. CGS unit dyne per centimeter square. Atmospheric unit ATM is the pressure exerted by the atmosphere at the sea level. It is the common unit of pressure, and 1 atm atmospheric pressure is 1.013 into 10 raised to power 5 pascals. Let's solve a numerical. The two thigh bones, each of cross-sectional area 10 centimeter square, support the upper part of a human body of mass 40 kg. You have to find out the average pressure sustained by the femorus. Here, the total cross-sectional area will be 2 into 10 centimeter square. That means 20 into 10 raised to the power minus 4 meter square. The force acting on them is 40 kilogram weight. That means 400 Newton. By taking the value of G as 10 meter per second square, this force is acting down and hence normally on the femorus. Thus, the average pressure is 2 into 10 raised to power 5 Newton per meter square.